Intel could have been a pioneer in the trillion-dollar AI race and let it slip away. And the strangest part is, it wasn't a loud mistake. It was a quiet decision inside a lab. In the next few minutes, you'll see the exact moment that window closed. In the spring of 2007, Intel held a position that few companies in the history of technology had ever occupied. Its x86 processors ran inside roughly 80% of the world's personal computers. Its server chips powered the expanding backbone of the Internet. Its name was synonymous with computing itself. The company's revenue that year exceeded $35 billion, and its engineers spoke openly about a design philosophy that had served them well for 3 decades. If you built a fast enough general-purpose processor, the world would find a way to use it. That philosophy was not arrogance. It was, by every available measure, correct. But inside Intel's labs, a project was beginning to take shape that would quietly expose the limits of that thinking. It was called Larrabee, and the choice Intel made about what to do with it was the decision that cost billions. The architecture of Intel's dominance had been built on a simple premise. Sequential computation, one instruction executed at a time, at ever-increasing speed, was the engine of progress. The x86 instruction set, born in 1978 and expanded with each generation, had become the universal grammar of modern computing. Every laptop, every corporate server, every government database ran on derivatives of that same design. By the mid-2000s, Intel had refined this model into something close to an industrial religion. Its manufacturing cadence, the famous tick-tock cycle of alternating silicon improvements and architectural redesigns, kept it perpetually ahead of competition. The company's internal culture rewarded those who served the CPU roadmap. Divisions that contributed to x86 margin were powerful. Divisions that challenged the primacy of that margin were not. Graphics chips occupied a strange and uncomfortable position in this world. Nvidia, founded in 1993, and ATI, which AMD acquired in 2006, had built processors optimized for a fundamentally different kind of work. Not one instruction at a time, but thousands of simpler calculations running simultaneously. Parallel processing. The GPU was a niche product Intel's leadership believed. It was built for gaming, for rendering polygons on a screen. It was not the future of serious computing. That belief was not irrational. It was simply incomplete. The Larrabee project, which Intel began developing in earnest around 2006, was an attempt to build a many-core chip that would combine CPU programmability with GPU-level parallelism. The internal pitch was appealing. Instead of ceding the graphics market entirely to Nvidia and AMD, Intel could build something that straddled both worlds, an x86-based GPU, a chip that programmers already trained on Intel's architecture could use without relearning everything they knew. Engineers who worked on Larrabee described it as technically audacious. The chip would pack dozens of modified x86 cores onto a single die, each capable of running vector operations at scale. Pat Gelsinger, then the chief technology officer at Intel and one of Larrabee's internal champions, later told the Computer History Museum that the project had been pointed at precisely the right target. His words, recorded in a 2019 oral history. "We were in the right space, and had Intel stayed with it, the world of machine learning, AI, Nvidia would be a fourth the size they are today. But Larrabee was falling behind. The software stack required to make the chip competitive with Nvidia's already mature graphics offerings was not coming together on schedule. The silicon itself, demonstrated at Intel's developer conference in San Francisco in the fall of 2009, drew a lukewarm response. Die size was excessive, performance numbers for graphics workloads were unimpressive, and crucially, the team comparing Larrabee against the current generation of Nvidia hardware was comparing it against the wrong benchmark entirely. In December 2009, Intel officially announced that Larrabee would not launch as a consumer graphics product. By May 2010, the GPU ambition was formally buried. The technology was recast as a high-performance computing research platform and passed on to what would eventually become the Xeon Phi coprocessor, a product aimed at scientific computing clusters. not at the broader market. The project was over. The window, though no one could see it clearly yet, had just closed. What Intel's leadership did not fully register in 2009 and 2010 was that a separate chain of events was already underway that would transform the niche problem of parallel processing into the defining challenge of the next 2 decades. At the University of Toronto, a researcher named Geoffrey Hinton had spent years working on neural networks, computational systems loosely modeled on the structure of the brain, capable of learning patterns from data. The work was mathematically intensive and had repeatedly stalled against the limits of available hardware. Training even a modest neural network required performing millions of matrix multiplications simultaneously, a task that CPUs handled poorly and slowly. Nvidia's GPU was structurally almost ideal for this kind of work, not because Nvidia had designed it for that purpose, but because the same parallel architecture that made it efficient for rendering game graphics made it efficient for the matrix algebra at the core of deep learning. In 2007, Nvidia had released CUDA, a programming platform that allowed developers to write general-purpose code for its GPUs without going through a graphics API. The stated audience was scientific computing researchers. Jensen Huang, Nvidia's founder and chief executive, had committed to the platform despite years of uncertain commercial returns. CUDA was expensive to build, difficult to justify on quarterly earnings calls, and produced no immediate revenue. It was, by any conventional financial analysis, a distraction from Nvidia's core gaming business. It was also, quietly, a trap being set. In 2012, a team at the University of Toronto trained a deep convolutional neural network called AlexNet on 2 Nvidia GTX 580 graphics cards. They entered it in the ImageNet Large-Scale Visual Recognition Challenge, an annual competition that tested machine recognition of objects in photographs. AlexNet won. It did not merely win. It won by a margin that broke the competition's frame of reference, reducing the leading error rate from roughly 26% to 15%. Researchers who had spent careers building handcrafted image recognition systems looked at those numbers and understood immediately that something had changed. The hardware that made AlexNet possible was not an Intel server. It was 2 consumer gaming GPUs connected in a university lab. The academic community moved fast. Within months of the ImageNet result, research groups at Google, Microsoft, Baidu, and dozens of universities began porting their neural network experiments onto Nvidia hardware. They found what the Toronto team had found. Training times that took weeks on CPU clusters collapsed to days, sometimes hours on GPUs. The speedups were not marginal. They were, depending on the workload, between 10 and 100 times faster. CUDA was the reason the transition happened cleanly. Nvidia had spent 5 years building a software ecosystem, optimized libraries, compiler tools, documentation, developer relations, that made its hardware accessible to researchers who had never written graphics code. The switching cost for a lab already running CUDA was low. The switching cost for a lab that wanted to move to a different platform was not. Intel had no equivalent. Its Xeon Phi, the descendant of Larrabee, required a specialized programming model that sat outside the research community's existing workflows. Its standard CPUs, however fast, could not compete on parallel throughput. The infrastructure of deep learning was being built, layer by layer, on Nvidia's stack. Inside the major technology companies, the shift was already visible in the infrastructure decisions being made at the data center level. Google began designing its own AI accelerator, the Tensor Processing Unit, in 2013, partly in response to a projection by its own engineers that if even half of Google's users used voice search for 3 minutes a day, the company would need to double its entire data center footprint using existing CPU hardware. That was a projection for one application at one company. Amazon, Microsoft, Meta, and Baidu were running similar calculations. Every major internet platform that had invested heavily in recommendation systems, content ranking, and search relied on the same class of matrix algebra that GPUs handled efficiently. The migration of data center workloads from Intel heavy racks to GPU-accelerated clusters began slowly, and then, after 2016, accelerated sharply. The irony was structural. Intel still provided the server processors, the CPUs that managed memory, storage, and network traffic inside every major data center. It was still the foundation of the physical infrastructure. But the actual computational work, the operations that determined what a user saw in their feed, what ad appeared on their screen, what search result ranked first, that work was being performed by Nvidia hardware. Intel built the house. Nvidia was the engine inside it, and the engine was becoming more valuable than the house. Intel's leadership recognized the problem, but the response was fragmented in ways that became characteristic. In 2016, the company acquired Nervana Systems, a startup building custom AI chips, for approximately $400 million. Nervana's design was technically ambitious but architecturally narrow, optimized for specific neural network workloads in ways that limited its flexibility. Intel announced plans for a Nervana-based product called Lakecrest and then, within 2 years, quietly abandoned it. In 2019, Intel acquired Habana Labs, an Israeli startup that had developed an AI training processor called Gaudi, for approximately $2 billion. The Habana technology showed genuine promise. Amazon announced in December 2020 that it would use Gaudi chips to train large language models in its cloud infrastructure. Intel described the announcement as the first crack at Nvidia's dominance in GPUs. What happened inside Intel after that acquisition became a case study in organizational friction. Habana had operated as a startup where consequential technical decisions were made quickly, in hallway conversations by small teams with direct accountability. After the acquisition, former Habana engineers described a new reality. Decisions that had taken minutes at the startup now required multiple meetings with dozens of participants. Habana was placed not under Intel's GPU division, but under its data platform group, creating a parallel structure where two competing AI architectures, Gaudi and the GPU-based Ponte Vecchio, were developed simultaneously, with overlapping resources and no clear mandate. The original founders and senior engineers of Habana Labs began leaving Intel. Most departed as soon as their 4-year retention agreements expired. By 2024, virtually the entire founding team was gone. In January 2025, Intel announced that Gaudi had missed its projected $500 million revenue target for 2024. The next-generation processor, Falcon Shores, received negative customer feedback and would not be commercially released. Development beyond Gaudi 3 was halted. The acquisition that was supposed to end Intel's AI deficit had produced no durable competitive position. The Nervana investment was gone. The Habana investment had not scaled. Ponte Vecchio, Intel's GPU effort aimed at the high-performance computing market, was discontinued. Each initiative had been pursued in parallel, with divided resources, without the unified software ecosystem that gave Nvidia's platform its compound advantage. The software dimension of this story cannot be separated from the hardware. CUDA, by the mid-2010s, was no longer simply a programming tool. It was a platform that had accumulated years of optimized libraries, QDNN for deep neural networks, QBLAS for linear algebra, NCCL for multi-GPU communication, that made Nvidia hardware not just faster, but more accessible. Every graduate student who learned to train neural networks learned on CUDA. Every research paper that benchmarked a new model benchmarked it on Nvidia hardware. Every major deep learning framework, TensorFlow, PyTorch, JAX, was built with Nvidia's architecture as the primary target. Switching away from that ecosystem was not simply a matter of buying different chips. It required rewriting or revalidating software libraries, retraining engineering teams, and accepting a period of reduced performance during the transition. For hyperscale customers running continuous model training at scale, the cost and risk of that transition were, in most cases, prohibitive. Intel's software response was never unified. Its AI software efforts were distributed across multiple divisions, product lines, and acquired companies that had not been integrated. The developer tools for Gaudi, for Ponte Vecchio, for the Xeon Phi, for Intel's integrated graphics were separate ecosystems, each with partial documentation and limited community adoption. Nvidia's moat was not a wall that Intel could breach with a single acquisition or a single product cycle. It had been constructed across a decade of consistent developer investment, and it compounded with every model trained, every library optimized, every research paper written on that platform. By 2021, Intel still held approximately 68% of the combined AI and data center revenue pool when measured against Nvidia and AMD. That number obscured a trajectory that had already become irreversible. In the 12 months following the public release of ChatGPT in late 2022, the demand for AI training and inference hardware at scale accelerated beyond what most forecasts had projected. Every major cloud provider began expanding GPU capacity as fast as supply chains would allow. Nvidia's H100, built on the Hopper architecture, became the most constrained product in the semiconductor industry. Lead times stretched to months. Prices for H100 clusters on the secondary market exceeded list prices by substantial margins. Intel had no equivalent product to offer. By late 2025, Nvidia's share of the combined AI data center revenue tracked against Intel and AMD had reached approximately 86%. Nvidia's quarterly data center revenue stood at roughly $51 billion. The combined data center revenue of Intel and AMD was approximately $8 billion. Intel's stock fell more than 50% in 2024 alone. In November of that year, Intel was removed from the Dow Jones Industrial Average, an index it had joined in 1999, and replaced by Nvidia. The stated reason from S&P Global was that Nvidia was more representative of the semiconductor industry. In December 2024, CEO Pat Gelsinger, who had returned to Intel in 2021 explicitly to execute a manufacturing turnaround, retired under pressure from the board. The decision that cost billions was not a single moment. It was a series of organizational choices made across roughly 15 years. The cancellation of Larrabee, the failure to build a unified software platform, the fragmented acquisition strategy, the structural inability to prioritize a market that had not yet generated revenue over a market that had already generated decades of it. Each individual choice, reviewed in its own context, had a rationale. The targets, the margin pressures, the manufacturing roadmap, the competitive environment at the time, none of it was irrational. The records show that the consequences emerged not from a single error, but from a pattern of decisions made by a company that had built its identity around winning a specific kind of competition and had not created the internal conditions necessary to recognize when the terms of that competition were changing. In 2025, Intel's new chief executive, Lip-Bu Tan, began restructuring the company's operations. Nvidia disclosed a strategic investment in Intel. SoftBank and U.S. government manufacturing incentives provided additional capital. Intel's stock recovered modestly. The Gaudi line was discontinued. The data center GPU effort was wound down. The company announced it would focus on its manufacturing business and on its core CPU roadmap. Somewhere in the archived internal records of the Larrabee project, the performance benchmarks, the engineering reviews, the budget justifications from 2008 and 2009, the full shape of what was lost is still partially visible. Not what Intel failed to invent, what Intel had already built and chose to set aside. The filings, the acquisitions, the quarterly reports, the org charts, they are still there. All of it, still there.